This is Further Mechanics 2 from 2022. First question is, I think, the first of 4 centre of mass questions, which is a bit excessive. This is one of the nice ones. It's just x bar times the total mass, which is 2m plus 3m plus km, is equal to 2m times 3a plus 3m times a plus km times minus 3a. And you sort this out, you divide by this, and you get that. It's sort of like taking moments. I mean, it is taking moments, isn't it? But it's sort of like, it feels like the same idea as well when you're doing it. But of course, then we have exactly the same for y bar, except it's the same over here. And then over here, it's going to be this times that, plus this times that, plus this times that. And you get this similar expression. You could have also done that in vectors, as a vector form as well, to get them both at the same time, but sure. Given the distance from the origin is this, well, the distance from the origin is x bar squared plus y bar squared square rooted. So if we square both sides here, I mean, put these two things in here and square both sides, we'll get a ninth a squared is equal to these two things added together. But you can cancel the a squareds because there's an a squared in here and here as well, so we'll just cancel those out. This is this squared over 5 plus k squared, and likewise over here, so we just put that 5 plus k squared over there, and then of course we can put the 9 over on both of these. Eventually, when you do a bunch of expanding and stuff, you actually, and dividing and through and stuff like this, you get to this. Whenever you're happy with a quadratic, you can just put it in a calculator, so you didn't have to get the numbers this low, you could just put something in a calculator eventually and you get these two answers here, which will be the answer to the first question, so that's good and done. Question 2 then is about F equals ma. We've got mass 60, we've got 200 watts, so power is over velocity is the force, so divide by v, so force is 200 over v. And then we can set up F equals ma, so this minus the resistance, so 200 over v minus 3v squared, is equal to m. Now they want this in terms of x's, so we can break out this formula here, mv dv by dx. The other one is m dv by dt, but they're not asking about that yet, so we just want this one here. And so we'll put this in, so this v is just v, the m is 60, dv by dx is here. This is what I said, it's this one minus this one. And yeah, we can just combine those two fractions together, we can divide by 60v, and we end up with what they wanted us to get. Distance travelled is this, between 2 and 4 meters per second. So what we want to do is we want to solve this differential equation, so times by 60v squared divide by this object here, we get this. This is just integrable, because the denominator differentiates to something of the form of the numerator, so this differentiates to minus 9v squared, which I can sort of change into that just with some constants. So this just integrates to a log. This of course integrates to x. This integrates to a log, and because of this actually goes to 9v squared, or minus 9v squared, doesn't it? If I just bang a 60 over 9 with a negative in front, I think this is now perfect, because if you imagine differentiating this, you put this on the bottom, the differential of this is minus 9v squared, which goes at the front, 9's cancel, the negatives cancel, and then you just get 60v squared. Plus c doesn't really matter. I'm just going to substitute in v is 4 to find an x, and v is 2 to find an x, and then I can just do this value minus this value. Minus minuses go to a plus, and then the c's will obviously cancel. You could have literally just integrated between 4 and 2 if you'd wanted to. That also works just fine. Of course, when we do, this is the plus log, and then this is the minus, so it's this divided by this following log laws, and we end up with this here as our answer. Question number 3 then is our second centre of mass question. I'm highlighting these rows, or these lines here, because my English teacher taught me to highlight when I was younger, and so I've carried that lesson through with me in life. This just says that these bars are twice as heavy as the other bars. So when I'm doing exactly the same formula I broke out earlier, which is x bar times the total weight of the system, or mass of the system, I'm going to say this 10A is just this 10A, and then there's a 8A here, there's a 6A here, and then there's 2 lots of 4A plus 5A plus 3A, because these are all twice as heavy. That equals, and then I'm just going to do distances times masses of all of the different ones here. So 0, the distance from this 6A to the line AC, because we're taking this from the line AC, is 0, so that's 0 times 6A. And then the distance here is 2A across, so that's the distance. And then the mass is 2 times 4A, because this again weighs twice as much. And then this one is 2 times 3A times this distance of 4A. This one here is, well, the centre of mass of this diagonal bar is going to be 2A along, because it must be in the middle there, so it's in the middle of 4A, so that's 2A along, and then of course 2 times 5A. This one here I think is the 4A times 8A, and then this one here is this 10A bar has centre of mass 4A along, so just 10A times 4A. You sort that all out, you eventually end up with this, and that'll be our answer. I hope. Anyway, so that's that done. The mass of the framework is m. Particle of mass km is attached to E, so that just goes there. Mass km going downwards. When it's freely suspended from F, CE is horizontal, so it suspends down like this. So therefore, the centre of mass of the framework, which is somewhere over here, 2.75a across from AC, which therefore means 4a minus this is 1.25 this way from this line. The moment here, so w times this, is equal to the moment here, which is 4a times kw. So we can just set it up. Sorry, km, because they've said sorry, it's about mass, isn't it? Oh, which means, of course, I should have put some g's in here. So it's mg and kmg, but of course the g's would cancel, so it doesn't really matter. You end up with this eventually, and because they're balanced, because of course this is going straight down, so that's kind of the way that I decided to do it. Anyway, question number 4 then is our horizontal circle question. There'll be a vertical circle question later. The thing that I like about mechanics exams is, of course, you can basically predict every question you're going to get before you open the paper, which is nice. Tan theta is this, so imagine a triangle, opposite side 8, adjacent 15. The 8, 15, 17 triangle exists in this world. So sine theta is 8 over 17, and cos theta is 15 over 17. Draw the triangle if you want to. Just don't work out this theta, because you just lose street cred if you do that. So we have this here. Let's start putting some forces in the diagram. This distance actually first, I'll say, is, I didn't actually need these, but tan theta is this over that. So this times tan theta is that. This times tan theta, 6 times this, is just 16 over 5a, I think, because you do some cancelling. Does that make sense to in my head? Yeah, you do some cancelling, you get this eventually. So that's good. So that's just from SOHCAHTOA. Now some forces then. We've got mg going down, we've got a tension going this way, and we've also, read the question carefully, this string goes through this thing here and then to there. So it's the same string, which means the tension here is the same as the tension going across like this. And now this tension is not nice because it's not going horizontally or vertically like the other ones are, so let's break this tension up upwards. Of course, this angle is just theta by alternate angles, so this is t cos theta, which is t 15t over 17, and then this across here is t sine theta, which is 8t over 17. And now we can start resolving for forces. We have this 15 over 17t is equal to mg, and that's actually just the first thing that I was asked to do is find g in terms of the other things. And now, more interestingly, we can do F equals ma going towards the center. So F equals ma. Now a, if you're given the angular velocity of omega, which is what we want to find, a is equal to omega squared r, where r is the radius of the circle it's going around, which is this number that we got earlier. So, okay, we can put that in there and this r in for there, and we can put the F in, because the force is going to be t plus 8 over 17t, t sine theta, because they're both going towards the center. And that's equal to m times omega squared times r, which is, I think, what I've got all here. T sine theta is, of course, just 8 over 17t, as I said. T itself is 17 over 15 mg, so that all goes in there as well. You sort this all out, all the m's cancel, of course. You do some more sorting out, and eventually you end up with that there. Good, so that's the 4th question done. Another centre of mass question. So we have this from the formula book. It says the sector of a circle has centre of mass this from the centre. So I can find the centre of mass of this. The radius is 3a. The angle here is pi over 2. But we need 2 alpha to be pi over 2, so we need alpha to be pi over 4. So we'll put both of those figures into there, and we'll end up eventually with this. So that's the distance to the centre of mass from the centre of the pretend circle going all the way around. Now, that's not actually what they've asked me for. They've asked me for the centre of mass from OC. But of course, this is going to be an isosceles triangle here. This will be pi over 4, 45 degrees here. So what I can say is, if I want this distance here and just call it d, this d squared plus this d squared, which is the same because it's just an isosceles triangle, right-angled, is equal to this thing squared. So I've actually called it r, I remember now. So we've got this squared plus this squared equals this squared. I've worked out this distance here based from this formula. We can just square this for that, we can divide by 2, and we can square root, and we'll get what they wanted me to get. So that's good, so that's this distance here, so I'll put that into there. Find the distance from the centre of mass from FC, from the entire thing. So we've got 2 more centre of masses to consider here. The centre of mass of this box, which is of course just 3 over 2a away from here, or 1.5a, and this one here, which is also 1.5a, the other direction. And now we can sort of do the same thing we were doing in question number 1, which is we can say x bar, so the distance from FC horizontally, times the entire mass. We can model the mass as just the 3 areas added up, so 9a squared plus 9a squared plus the area of this. Now, r is 3a, so that's 9a squared, and then you times it by pi because it's pi r squared, and then you divide by 4. because it's a quarter of a circle. So that's the total area, which we can sort of model as the mass. And then we have 1.5a times the area of this one, minus 1.5a times the area of this one, because that distance is a negative, we can say, and then plus 4a over pi times the area of this one. And of course we can just sort this all out. These cancel, which is very kind of them. The pi's cancel, some a's cancel, all good stuff. We get this. We can times everything by 4 is probably what I did. And then if you times everything by 4, you can then divide everything by 9, and you end up with this eventually. So we have that, which is, oh, they didn't, yeah, sure. So we have that. Okay, so we have that there. That's just this figure here. So that's the distance. Now this is the combined center of mass I'm modeling here. Now if we hang this thing from F downwards, the angle here, theta, is the thing that we now need to find. So what I need to do is I need to find this, I need to find the y bar, right? So I've got my x bar. If I could find my y bar, then tan theta would be this over this, because of course it always hangs through the center of mass. Now apparently you can use some symmetry here, but I can't really bother to think about why. So instead what I just did was found y bar by copying and pasting some slides that basically look exactly the same. So we've, considering the two center of masses here, the center of mass of this one is 1.5a downwards. The center of mass of this one is 3 plus 1.5a downwards, which is 4.5a. And the center of mass of this one is 3a plus that same, remember this 4a over pi thing we had earlier? To find that, we did some Pythagoras. So that's 4a over pi, and so is that. So therefore, when I got to here, I just did 3a plus that thing there to find the y center of mass of this bit here. Same ideas with these areas and masses here. We sort this all out, we get this, we do some more sorting out, we divide everything by 9, we end up with that. And now, of course, tan theta is equal to this divided by that. We can cancel these two things, which often happens in questions like these. We can here, the a's all cancel out, which is really nice. This is just a number, do tan inverse of it, and we end up with that there. I promise this is the last center of mass question on this paper. But okay, it's one of the integration ones. So firstly, we need to find the total mass of this cone, or yeah, it is going to be a cone when we do it around. So of course, it's an integral of a solid of revolution, so it's going to be pi integral between 9 and 0 of y squared dx, except you also need to throw in, the lambda x, which is modeling the non-uniformity of it. So it's just my regular pi integral of y squared dx, but I also need to throw in this because, of course, density is mass over volume. So density, which is essentially what this is, times the volume is equal to the mass. Does that make sense? Yeah, it does make sense in my head. And then you just put this inside here and do the integration with it. So we sort this all out. Of course, that makes x cubed altogether over 9. Raise it to a 4 divided by 4, which makes that. Yeah, I agree with that. We put the numbers in and we end up with this. And then we need to use the formula now, which is this one here. It's the integral of x, y. The standard integral is integral of x, y over integral of y. But of course, we've got a few adjustments to make there. We've got to throw in the lambda x again, just like we did before, because again, we just need to model the density in there. And we're also doing pi y squared in here, but at its roots, this is just the integral of x, y over integral of y idea. It's just been adjusted for the volume of revolution and for the density that we need to throw in as well. Of course, this bit here is always just the bit that we found by doing this thing, so I can just put that straight in there. And now I can do this integral. I can bring out the lambda and the pi, which then cancel with this 2 lambda and pi. We can integrate that, of course. We can do, there's lots of numbers that you can type in and have fun with, but you end up with that eventually. And that's the distance from here to the center of mass in this direction. Now, a hemisphere has been shoved on the end of this. So you imagine you've got a cone now, and then you can put a half sphere on the end of it like this. And apparently, no matter where you put that down on the surface of the hemisphere, it always just stands up straight. So I decided to consider this scenario here, where you've just got a tiny, tiny part of the hemisphere touching the ground here, and it's just standing in equilibrium like this. And now what I've can learn from this is that the center of mass of the cone is, of course, if it's 7.2 this way, then it's 1.8 this way. And the center of mass of the hemisphere, that's in the formula book, it's this. And of course, r is 3, because it has to be to make it fit on there. 3/8 times 3 is 9/8. And now, if it's standing in equilibrium here, which it says that it does, then where does it even say that? I'm trying to read the question in rest. Okay, then that means taking moments that 1.8 times this weight, which they've just given us as W now, is equal to 3/8 times 3 times this weight, which is just kW. And you can cancel the W's, you can times these along, and you get K as this, which will be our answer. You could have modelled that anywhere else, but I thought that was probably the easiest place to do it from. Question number 7 is the vertical circle question. I did say we'd get one of these, so let's first look at this here. So we've got obviously an mg coming down when the particle ends up here. We've got mg there, we've got tension there. That means going this way we've got mg cos theta, because that theta is there by corresponding, and then you've got a right angled triangle here, and that's next to it, so it would be cos theta. We're not told anything about theta at all, which is fine. What we need to do next is we can say, of course, its speed v is here. We can set up F equals ma, where a is equal to v squared over r. If you're given, this is not the angular speed, this is just the actual speed. So it's the v squared over r formula. F equals ma says t minus this equals m times this a here. And of course, r is 2a over 5, so that goes in there. So we have all this, and okay, that's fine. We can do a little bit of tidying up there. I've written this a bit weirdly, but that's only because I know what's coming next, so I've just left that like this. Now v squared, we obviously want to write t in terms of u, so how do we connect u and v based on this here? Well, we can just use the energy balance kind of ideas. So initially it has kinetic energy half mu squared. At its last point here, it has kinetic energy half mv squared, but it also has potential energy based on how much it's risen, which is this much here. So okay, well, how much is this? Well, this much here, if you draw a little triangle like this from here across, this here is obviously just the hypotenuse is 2a over 5, so this will be 2a over 5 cos theta, which means this here will be 2a over 5 minus 2a over 5 cos theta. That will be this distance, the height that it goes up by. So therefore we get this, the initial kinetic energy is equal to the final kinetic energy plus the gained potential energy. We can do some timesing up and factorizing out and stuff. This is not too complicated. We can cancel some stuff now, we can move some stuff over. And here's my 5v squared, which I'm just gonna throw this straight into there. I'm going to expand out and just magically, of course, when you add this amount into there, you just get 3 of them, and so you just magically end up with exactly what they wanted you to get, which is great. So that's that done. Given that it moves in complete circles, now it's a string here, if you read earlier, so it's a string. So to move in complete circles, you just need the tension in the string to never be 0. As soon as the tension in the string is 0, it will just collapse in and fall down like this. So we just need the tension to always be greater than 0, and the worst or the most dangerous point, it's not really the right word, is right at the top. So let's just model theta to be pi and say that we still need the tension to be greater than or equal to 0 even up there. So okay, let's just set this thing here to be greater or equal to 0, and we'll set theta to be pi. And when you sort this out, you end up skipping a term apparently. There should be some working term in here, which is totally gone missing. Apologies for that. Let's bring this right up to the front. This is so unprofessional for a person who has nearly 2k subs. But yeah, this goes in there, perfect. And yeah, I mean, this just becomes a 1, and then you take this away, and then you times everything up and square root, and we actually end up with this here. Good, so that's that. Given u is this thing here then, find the magnitude of the acceleration when OP is horizontal, so we're here. Now, there's a few ways of doing this, including using this thing again, which I didn't think to do because I figured we'd already used it here, so it just didn't occur to me to use it again. So what I did was I did some more energy stuff. I said if u is this, then and the height gained, if you'll get to there, is this, then that means half m u squared with the initial speed here equals half mv squared plus that potential energy that's been gained, and you can work out v from there. Eventually you get v is this, v squared really, but you get v as this. And then I said acceleration to the center is the same thing we saw before, v squared over r. So the acceleration to the center is this divided by this, which is this. And so that's my acceleration this way. Of course, I have my standard acceleration downwards due to gravity of just g, and therefore my magnitude of acceleration is just 8g squared plus g squared square rooted, and we'll end up with root 65g as one of our answers. You could have used this formula again. You could have set theta to be pi over 2, and you could have used this formula again to work out the tension, and then used F equals ma to get the acceleration. But anyway, apart from including air resistance, just a way you could make it more realistic, you could model particle as actually having dimensions and not be a particle. It's a very standard response to that, so that's good. Question number 8 then, about simple harmonic motion. You knew this question was coming up because it always does. This made me laugh. That's just incredible. Anyway, so we draw it down, and we've got mg coming downwards here, 0.5 g. We've got tension, which is modeled via this formula. And now what I want to do is find the equilibrium point, of course, first. So we set tension to be 25x over 1.25. And we'll set this equal to this to find the equilibrium point. We get x as this, using g as 10, remember, makes this 5. And we get x as that. So that's the stretch in equilibrium. So that's really useful for me to know. And now I can model simple harmonic motion by saying the force, this should say F. Apologies, that's again unprofessional for a person with so many subs. This should say F. And of course the force is T, which is this, minus this, and that needs to equal 0.5x double dot. Now the T here, I'm just going to take some random point during its journey of simple harmonic motion where it stretched some extra x downwards. This x is not equal to this x. I'm being super confusing here. Apologies for that. This is the equilibrium point, which is there. So that's the stretch that it basically always has. And this is any extra movement away. This is the displacement from the equilibrium point. So I'm being super confusing here by making my x's very unclear, but hopefully over the top here I've at least made that a little bit clear, that this just means this extra stretch from the equilibrium point, which is here. Take away that equals minus 0.5x double dot. As a general hint, obviously you want this number that you get to cancel with this number, which I do get. You also want a negative here, so if you're not coming out with a negative, just randomly throw a negative over here to make it work, and you'll get 4 marks. So that's good. So just always, you just need to fiddle with this until you get this cancelling with this, and until you get some negatives over here. So omega squared is 40, and you just have to say this is simple harmonic motion with omega squared 40. Period is 2 pi over omega. So omega is root 40 is 2 root 10, the 2's cancel, and we get pi over root 10, which is fine. Maximum kinetic energy is that. Super useful formula, this, super useful. Go into your exam knowing this formula, and also go into your exam knowing that maximum velocity, you can see it from this formula, happens when x squared is 0, or when x is 0. Maximum velocity in simple harmonic motion happens when you're at equilibrium point. So we can put x as 0 into here. We can use this and a half mv squared to know what v is, which is this, and we can put that into here, and we'll get a squared is this, which means a is this. Using omega squared again is 40, and here, so that means that the amplitude of simple harmonic motion is 0.5. So that means from the equilibrium point, this was brought down 0.5 meters. Now, A to B is what they're asking for. The natural length is 1.25. The equilibrium point was another 0.25, so that takes us to 1.5. And then we have an amplitude of 0.5, that takes us to the full 2 meters that they wanted us to get. Apologies for having such a mess on the board here. I'm about to delete it all, I think. Yes, I am good. The particle B returns to B t seconds after it was released. Now, you have to figure out what this is really asking for a second. This simple harmonic motion doesn't last forever, because simple harmonic motion, this is a string, not a spring, essentially. So when you pull it down, the string wants to pull back up again, but when you really reach the point where the string is slack, there's no force springing up. So what happens is it follows simple harmonic motion until the string is slack. Then it just follows regular laws of motion, and then when it reaches the point where the string is taut again, then it will follow simple harmonic motion on its way down again. So what we need to do is we need to break this into sections. We need to find how long it takes using simple harmonic motion stuff to get to the slack point. Once it's at the slack point, we need to do some general equations of motion stuff to find out how long it's there for, and then we go back to the simple harmonic motion until it comes all the way back down again. So we don't just use this, you don't get 5 marks for just writing this down, because it doesn't follow simple harmonic motion for the entire time. So okay, its slack at x is minus 0.25. When it's 0.25 upwards, remember, because that's the equilibrium point, when it goes 0.25 upwards, which is minus 0.25 in terms of displacement from the equilibrium point, that's when the string gets slack. So let's find the amount of time it takes to get here. This is a super useful formula to know, because they always seem to ask with the weight at the end, so you use cos here. You put these figures in, we know what A is, we know what omega is, we solve for t, we get this. So that's how long it takes after you release it from rest to get upwards to the point where it's slack. Now that it's slack, we can't follow simple harmonic motion. So what we'll do is we'll work out the speed that it's going. And again, we can use this formula for that. That's super useful. This could really be a minus 0.25 squared, but of course that squares to the same thing. We put in these figures, and we get v as this. And now we just follow suvat, right? Because there's nothing going on with this particle aside from g bringing it down. So we just use suvat. We want the particle to go, it's got some speed going upwards. We want to know how long it takes to go up, and then stop, and then come back down to the same point where that string will be taut again, and then we're going to follow simple harmonic motion. So initial speed is this. Final speed will be the same thing going downwards. Acceleration is minus 10, according to this, and the time is what I want to know. We can use any of these formulas. I'll just use the top one because it's the easiest. We'll get t as this. So that's how long the particle takes once it's reached a slack point to go up and go back down again and reach the taut point again. And then what's going to happen, simple harmonic motion is symmetrical, right? So this t will be repeated as it comes back down to its initial position. So the answer will be this plus another lot of that, and we'll have our answer there. Thank you so much for watching, and I'll see you next time.